Hello, and welcome to this tutorial on equilibrium of a particle. In all the examples in this video, the particle or object is in equilibrium, and therefore the resultant force must equal 0. Here is example 1. An object of mass m kilograms is held in static equilibrium on an inclined plane by a force of 14 newtons, which acts up and parallel to the plane as shown in the diagram. Find the mass m and magnitude of the normal reaction force r correct to 2 decimal places. In this question it is assumed g equals 9.8 meters per second, where g is the acceleration due to gravity. Here is the diagram we are given. This is the object of mass m kilograms, and we can see the object is on this incline, which is at 30 degrees to the horizontal. As well, we have a force of 14 newtons going up and parallel to the plane, and we have the normal reaction force r, which is perpendicular to the plane. We now need to draw in any additional forces. Now if we look at this mass, we know that gravity acts vertically down on the mass, and the weight then is equal to the force due to gravity, which equals the mass of the object multiplied by g. And this formula here comes from Newton's second law, F equals ma, where the acceleration in this example equals g. If we now consider this force due to gravity, we can show that it's made up of this perpendicular component to the plane, which goes in the downwards direction, and this parallel component to the plane, which goes in the left direction, or again in the downwards direction. We note that the angle between these two components is 90 degrees, since we have a perpendicular and a parallel component. And in order to find these components, we need to find this angle here. To do that, we first extend this line, and note that the angle here is 90 degrees, so it's a right angle. And therefore, this angle here will be 180, which is the sum of the angles in a triangle, minus 90 minus 30. So that's 60 degrees. And then this angle, 60 degrees, and the angle that we wish to find, together makes up a right angle, because we have this plane and we have this perpendicular component, so the angle in between is 90. So then the angle that we wish to find equals 30 degrees. And actually we can show that this triangle here and this triangle here are similar triangles. Now we can find the perpendicular and parallel components of the force due to gravity. To do that, we need to use SOHCAHTOA, which is applicable to right angled triangles. What does that mean? Well, if we consider SOH, this means that the sine of an angle equals the opposite length divided by the hypotenuse. And in this force triangle, sine of 30 then equals the opposite, which is this parallel component of the force due to gravity, divided by the hypotenuse, which is then the force due to gravity. So we have sine 30 equals the parallel component divided by the force due to gravity, and since the force due to gravity equals mg, we can rearrange to show that the parallel component equals mg multiplied by sine 30. Now for the perpendicular component, we will use K. So the cosine of the angle 30 equals the adjacent, which is the component that we're after, divided by the hypotenuse, which is once again the force due to gravity. So then cos 30 equals the perpendicular component over the force due to gravity, and we rearrange this equation substituting Fg equals mg to find that the perpendicular component equals mg multiplied by cos 30 degrees. So now we've completed the force diagram, we can resolve the forces in a perpendicular and parallel direction to find the mass m and magnitude of the normal reaction force r. Starting with the parallel direction, we have two forces. We have this force here, mg sine 30 degrees, going down or to the left, and this force here, 14 newtons, going up or to the right. Taking this direction to be positive, we then have mg multiplied by sine 30 degrees minus 14 equals 0. And here the resultant equals 0 because in the question we're told that the mass is held in static equilibrium. Rearranging this, we have m equals 14 divided by 9.8 multiplied by sine 30. So here we've substituted g equals 9.8. And then plug in this into the calculator. This equals 20 over 7. And then to 2 decimal places, m equals 2.86 kilograms. Now we do the same, but in the perpendicular direction. So here we have this normal reaction force R, and we also have this component here, mg multiplied by cos 30 degrees. Taking the direction of the normal reaction force to be positive and resolving, we have R minus mg multiplied by cos 30 degrees equals 0. And then if we solve for R, we have R equals 9.8 multiplied by 20 over 7 multiplied by cos 30 degrees. So 9.8 is G, 20 over 7 is M. So here we've substituted the exact value for M rather than this solution to 2 decimal places, because we need to find R again to 2 decimal places, so we will round at the final step. And then we find that R equals 14 root 3. Once again, this is an exact solution, so to 2 decimal places, R equals 24.25 newtons. Here is example 2. A mass of 5 kilograms hangs from 2 light inextensible strings attached to a fixed horizontal ceiling. The string attached to point A is at an angle of 25 degrees to the ceiling, and the string attached to point B is at an angle of 45 degrees to the ceiling. Let the tension in the string attached to A be T sub A, so we read this as just TA, and the tension in the string attached at B be T sub B, and here we read this as just TB. Find TA and TB correct to 2 decimal places. And in this question it is assumed G equals 9.8 meters per second, where G is the acceleration due to gravity. The first thing we need to do is draw a diagram for this question. Here's a diagram. This is the mass of 5 kilograms, and we can see the string is attached to point A on the ceiling at 25 degrees to the ceiling, and this string is also attached to point B on the ceiling at 45 degrees to the ceiling. Now if we consider the forces for this diagram, if we just start by considering the mass, we have gravity acting vertically downwards, so we have the force due to gravity, which equals mg. And in this question we're given that the mass is 5 kilograms and g is 9.8 meters per second. So substituting these, we have 5 multiplied by 9.8 equals 49 newtons. If we just look at the question, we're told that the 2 strings are light and inextensible. So this is very important. What does that mean? Well, if the string is light, it means that it has no mass, and inextensible means that if you stretch the string, it doesn't increase in length. So in terms of the forces, it means that the tension force throughout each string is constant. And the tension force then pulls this string, so it acts in this direction in string A. So this is TA. And similarly in string B, it acts in this direction, so this is TB. Let's now consider the components that make up this tension force in string A. So the tension in string A is made up of this horizontal component going to the left and this vertical component going up. And to find this component, we first note that the angle between them is 90 degrees, and therefore this angle here equals 25 degrees since we have a pair of alternate interior angles. Now to find the components, we can use SOHCAHTOA again, or we can note that if a component includes the angle, then that component equals the resultant multiplied by the cosine of the angle, and if a component does not include the angle, then it equals the resultant multiplied by the sine of the angle. So if we look at this horizontal component, well, it includes the 25 degrees. The resultant is the tension in string A, TA. So the horizontal component then equals TA multiplied by cos 25, and therefore the vertical component equals TA multiplied by sine 25. Doing the same to tension in string B, here is the horizontal component going to the right, and this vertical component going up. Again, the angle between them is 90 degrees, so this angle here is 45 degrees. So once again we have alternate interior angles. And if we start with this horizontal component, well, it includes the 45 degrees, so then it equals TB multiplied by cos 45 degrees, and the vertical component then equals TB multiplied by sine 45 degrees. Now we've drawn all the forces and the components, we can resolve horizontally and vertically to find the tension in both strings. We start by resolving in the vertical direction. So we have this force here going up, that is TB multiplied by sine 45 degrees. We have another force going up, that is TA multiplied by sine 25 degrees. And going down we have the force due to gravity, which equals 49 newtons. So if we take this upwards direction to be positive, then TB multiplied by sine 45 degrees plus TA multiplied by sine 25 degrees minus 49 equals 0. And if we look at the question, since the mass hangs from the two strings, it must be in equilibrium. Then we just add 49 to both sides to get this equation here, and we call this equation 1. Next we will resolve in the horizontal direction, and here we have a force going to the right, that's TB multiplied by cos 45 degrees, and we have this force going to the left, TA multiplied by cos 25 degrees. Taking the right direction to be positive, we have that TB multiplied by cos 45 degrees minus TA multiplied by cos 25 degrees equals 0. And this we call equation 2. So now, if we just consider equation 1 and 2, let's just look at these first term in each equation. So we have TB sine 45 and TB cos 45. Now, sine 45 equals root 2 over 2. So TB sine 45 is just root 2 over 2 TB. And similarly, cos 45 degrees equals root 2 over 2. So TB cos 45 degrees equals root 2 over 2 TB as well. So if we take equation 1 and we subtract from it equation 2, we note that the first terms cancel. So then we're left with TA multiplied by sine 25 degrees minus TA multiplied by cos 25 degrees, and this equals 49 minus 0. So putting that together and factoring TA, I have TA multiplied by sine 25 degrees plus cos 25 degrees equals 49. Dividing through by sine 25 plus cos 25, we have that TA equals 49 over sine 25 degrees plus cos 25 degrees, and to two decimal places then, once we plug this into the calculator, we have that TA equals 36.87 newtons. So now we have TA. I suggest you substitute this exact value for TA into equation 1 or 2, rearrange to find that TB equals 47.26 newtons to two decimal places. Here is example 3. A smooth bead of mass m kilograms is threaded on a light, inextensible string attached to a vertical wall at points P and Q. The bead is held in static equilibrium by a horizontal force of 35 newtons. The string makes an angle of 30 degrees to the wall at P and an angle of 40 degrees at Q. And find the tension T in the string and mass m of the bead correct to 2 decimal places. And in this question it is assumed g equals 9.8 meters per second, where g is the acceleration due to gravity. The first thing we need to do is draw a diagram for this question. This is our diagram, and here is the bead. It is threaded on a light inextensible string attached to a vertical wall at points P and Q. So then this is the string which is threaded through the bead and attached to this vertical wall at the points P and Q. We are given that the bead is held in static equilibrium by a horizontal force of 35 newtons. So here is the horizontal force of 35 newtons. And as well we have that the string makes an angle of 30 degrees to the wall at P and an angle of 40 degrees at Q. So here we have an angle of 30 degrees at P and an angle of 40 degrees at Q. Now let's draw in the forces. We have this horizontal force of 35 newtons. We also know that gravity acts vertically down on this bead. So we have the force due to gravity, which equals mg newtons. And if we look at the question, the string is light and inextensible. So the assumptions that we had in example 2 hold for this example as well. But we are also given that the bead is smooth. And smooth then means that there is no friction force. So the tension force in this part of the string is equal to the tension force in this part of the string. In this part of the string then, we have the tension force which is pulling in this direction, and it equals T. And this is the same as the tension force in this part of the string, which also equals T. Now that we have drawn the forces, let's consider the components that make up this tension force on this part of the string. So the tension force is made up of this vertical component going up and this horizontal component to the left. We note that the angle between them is 90 degrees. So this angle here equals 30 degrees since we have alternate interior angles. And then to find the components we can use SOHCAHTOA, or we can note that this vertical component contains the angle 30 degrees and therefore it equals T multiplied by cos 30 degrees, whereas this horizontal component does not contain the angle 30 degrees, so it equals T multiplied by sine 30 degrees. Doing the same on the tension force on this side of the string, we note that it's made up of this vertical component going down and this horizontal component going to the left. Again, the angle between the two components is 90 degrees, so this angle here is 40 degrees since we have alternate interior angles. And then this vertical component, it contains the 40 degrees, so it equals T multiplied by cos 40 degrees. And since this horizontal component does not contain the 40 degrees, it equals T multiplied by sine 40 degrees. Now we can resolve the forces. Starting in the horizontal direction, we have this force here, T multiplied by sine 40 degrees. We have another force here, T multiplied by sine 30 degrees, so both of these are to the left. And this force here, 35 newtons, is then to the right. And taking the left direction to be positive, we have that T multiplied by sine 30 degrees plus T multiplied by sine 40 degrees minus 35 equals 0, since we're in static equilibrium. And then solving for T, we find that T equals 35 divided by sine 30 degrees plus sine 40 degrees. And because we need the answer to 2 decimal places, we have that T equals 30.63 newtons. Next, we resolve in the vertical direction. So we have first of all this force here due to gravity, Fg, which equals mg newtons. We have another force going down, T multiplied by cos 40 degrees, and we have this force going up, T multiplied by cos 30 degrees. So taking this down direction to be positive, we have that mg plus T multiplied by cos 40 degrees minus T multiplied by cos 30 degrees equals 0. And here we will substitute T as this value here, so the exact value before rounding. And of course G is 9.8. So once we've substituted and solved to M, we have that M equals T multiplied by cos 30 degrees minus cos 40 degrees divided by 9.8. And then after plugging this into the calculator, we find that M equals 0.31 kilograms to 2 decimal places. If you liked this video, please give us a thumbs up, leave your comments down below, and subscribe to this channel so you'll be the first to know when we release our next videos.